Let's move on to the next presenter of the day. I believe he's joining us via Zoom. So I'm not quite sure who's presenting. Kehinde Elelu, are you here? Yes. Kehinde, I can see you're going to be presenting, but I don't know if you're online.
Hello, everyone.
Okay. So in the interest of time, let's just get started. Please go ahead. Thanks.
Hey, Kehinde, can you start the presentation?
Yeah, okay. Yeah, so.
Okay. Okay. I'm not able to show my video, but should be fine. Can you check whether you can turn on my camera?
Okay.
We can see you now. We can see you and the slides.
So I am currently presenting with Tuan Lee.
Yeah,
He's unable to
I'm
share.
co-presenting this presentation with Kehinde. So but it should be fine.
Yeah, but you can't share.
Right, so,
I can't share photos. I can't share the screen. I can display a picture, your video. Yeah.
Okay, that's fine. All right, so hello everyone. This is Tuan Lee, assistant professor at Clemson University. So today I'm presenting this paper with Kehinde. He is my PhD student. And this work is entitled Direction of Arrival of Equipment Cells in Construction. So we're thankful to NSF and CPWR who sponsor for this project. So let's move to the next slide, Kehinde. All right, so this study, we tried to develop a new technology for enhancing the construction safety. Particularly, we want to develop a new technology to reduce the stroke by equipment hazard. So why this hazard is still a things that we need to deal with. So according to a lot of data, stroke by equipment remains the common hazards in construction, thus leading to a lot of accidents. For example, the BOS estimate that the contact with equipment hazard accounts for 15% of the total fatality in construction in 2020. And another study by OSHA estimated that 58% of the accidents in the time range from 1995 to 2008 is caused by stroke by equipment hazards. So as you can see there, this type of hazard is really main concern in our construction industry. Next slide. All right, so why stroke by equipment accident happens? So let's watch this short video on a scenario of stroke by equipment hazards.
Wheel tractor scraper was moving forward to get the ground ready for pad construction. There was no spotter at the site, and there was no internal traffic control plan in place. Before backing up to go over the ground again, the driver checked his rear view and side mirrors. He didn't see anyone in his mirrors, so he backed up. The driver's backup alarm didn't work, so the surveyor did not hear the scraper coming towards her. As the driver backed up, he ran over the surveyor. She died from the injuries. Let's look at the events leading up to this tragic incident and see how it could have been prevented. When a vehicle on a construction site has an obstructed view to the rear, OSHA's standard requires employers to provide that vehicle with a working backup alarm or a spotter on site to tell the driver when it is safe to back up. Now let's see what happens when protective measures are in place. Although there is now a working backup alarm, it is barely audible over the background noise. So as an added safety measure, there's also a spotter on site wearing a reflective vest. There's also an internal traffic control plan in place. This plan helps protect workers because it tells the drivers of moving vehicles and equipment the safest way to move around the work site. So this time, Before backing up, the scraper's driver waits for the spotter's signal, so he knows the area is clear to enter. Now, as the driver reverses, the backup alarm can be heard, and no workers are near the scraper.
So as presented in the video, you can see that, I mean, construction equipment is a great thing to have in construction. Construction equipment can help us increase productivity. We can do things faster, but construction equipment is a source of construction hazards, especially struck by equipment hazards. So the main causes of struck by equipment hazard is because workers and equipment, we share in the same workplace, and many scenarios, they sharing in really limited workspace. So they are working close to each other, and construction equipment is like with dynamic, it's moving a lot. So there's, the collisions happens pretty often to workers if the traffic is not well managed. So there's another reason why struck by equipment accident is popular in construction, because construction sites are pretty much noisy. There's a lot of sounds coming from many different types of equipment, like handheld equipment, excavators, cranes. So there are a variety of equipments, and they are making so much noise, and it is hard for them for the workers to listen to important sounds. So even though the construction equipment is working pretty close. Okay, I guess I now can. Okay, it's not showing up. Okay, so even though the worker is working really close to the mobile equipment, but they cannot listen to it because the impact of other background noise. And like another reason for struck by equipment hazard is the visibility during the nighttime. Especially in highway construction, we do in nighttime work a lot. So the workers, they are not able to see the surrounding objects well. That's why they're not able to avoid collisions with the construction equipment. So the struck by equipment are caused by so many factors, and we need to develop some things or technology to help the workers to detect surrounding equipment. And let's say if there's one equipment is moving towards the worker, so they should be able to recognize and avoid it. So let's see what we got in the literature. What are the technologies that we got in the literature right now? So from the literature, we found a few sensing technologies. So those proximity sensing technology are pretty much based on GPS devices or Bluetooth or imagery sensors like cameras. So they're using those kind of data to keep track the movement of the construction equipment. So there are some limitation of those technologies. So I listed here two main limitations of the existing technologies. The first limitation is the cost of those sensors. They are expensive because you have to install the sensors on every piece of equipment and even on the construction workers. So let's assume that if your construction project is complex, it involves many subcontractors. So you have to ask them to install those pieces of sensors on their equipment. And for some subcontractors, they are like small size companies and they are not afford to those expensive sensors. So it's pretty less applicable in the real world. And let's see. And then there's some other constraints like the visibilities and the obstacles. So So we need to develop new technologies. Kehinde, can you move on? So we develop a new technology using sounds. The reason why we use sound data for proximity sensor because it is not affected by visibility. So you can apply this technology in nighttime work, and it is indispensable. Let's move on to the next slide. All right, so this is the framework that we developed. So the framework use the audio as the input, and then using microphone arrays to detect the signals, and using the direction of arrival algorithms to process the sounds and allocate equipments. I'm gonna to hand it over to Kehinde. He's gonna to present some results, experiment results from this study.
So as I've already said earlier, the framework we use involved using the microphone array. The microphone array that we use for this experiment is Respica mic array version 2. It has 12 LED lights, it has 4 microphones, and it's connected to the Raspberry Pi. The Raspberry Pi is low maintenance, low processing device that can operate on low power between the range of 5 to 5 volts. And this can allow us to process this sound, the source of sound, to generate the local coordinate of the sound. So for this particular experiment, for the controller experiment that we did for this research, we locate 2 sound sources, which is the bulldozer and the hammer. Bulldozer is the mobile equipment, while hammer is the stationary equipment. So the figure you're seeing by the right-hand side shows the setup for the whole experiment. Each particular location is where the bulldozer moves from one particular position to another, which is the P1, P2, P3, and P4. And because we expect a stationary equipment like hammer to be used in a particular location for a long period of time, so we categorize hammer as an stationary equipment and is located at P4. So for the setup of this particular experiment, bulldozer move from each position to another, while hammer is stationary for the entire set of the experiment. So at each position, the bulldozer maintains a period of 30 seconds at this particular position, because when a bulldozer or any type of mobile equipment is operating on a construction site, it's expected to carry out an operation at that particular point. So the point we maintain for 30 seconds for this experiment is the point we expect the equipment to carry out the experiment. So the microphone array, as I've said earlier, is generating several local coordinate points of the sound source that is getting. And this, for the whole of the experiment, the local coordinate generated is between the range of 50,100 to 50,200, while for every 30 seconds, 1,000 local coordinate points is generated. With these local coordinate points, you can be able to calculate the direction of arrival of our sound, which we can use to determine the distance, as well as generate alert once a construction worker is inside the danger zone, according to what we show you in the framework. For the experiment, we measure the loudness of our experiment using a decibemeter, and the range of loudness is between 75 to 79. So the result of the bulldozer result is shown, where we move the equipment from one particular location to another. The result we got here is from the range of -1 to 1, and the local coordinate point for X and Y axis is positive for the first quadrant. So we basically divide this location of our equipment, which is stayed for like 30 seconds, into quadrants. And for the first position, the X and Y coordinate that we generated are positive. For the whole entire experiment, Z is the same and is positive throughout the experiment, because we didn't change the elevation of our microphone array. While after the first position, moving to the second position, the X value changed to a negative value, which means our equipment have entered the second quadrant. While for the third position, the equipment moved slightly in between the third and the fourth quadrant. While for the fourth position, the equipment moved to the fourth quadrant, and we have a X value of positive and a Y value of negative. As I've said earlier, the Z value is the same because the elevation did not change throughout the experiment. Once you change the elevation of the microphone array, the Z value will also be changed, and you will notice based on the result you get. So for the location determination of the armor, we notice it's slightly up and down in the result generated. And this is the kind of result we expected because the location of the armor and the construction site is stationary. And this equipment is telling us that where I'm getting the sound source from is stationary throughout the whole set of the experiment. So using this local coordinate point, you can calculate the direction of arrival of the sound. So calculating direction of arrival of the sound at each location, we average it for, we average the direction of arrival, which is the angle for each location. And the average for the first position is 1.47. For the second position is 1.006. And for the third position, 163. This is the average value because when you are generating the sound, you are using a microphone array to determine direction of arrival. The value
could you please wrap up quickly? I guess we can just go to the final results and talk more about that.
So this just shows the loudness of the whole experiment. You can actually generate the loudness of the sound also with our framework. Also, we plot a bulldozer map showing the movement of the whole entire bulldozer sound in the control environment. And we conduct this experiment 5 times to show how accurate our result is. And the darker positions are very similar and close to each other. So the conclusion of this whole experiment is we can use this framework to separate sound source, to track it and localize the source of sound. Once we get the location of sound, we can triangulate it to get the distance and properly alert the construction workers once they are located inside the danger of the warning zone. The practical implication of this experiment is because we are making use of microphone array and Raspberry Pi, which can be easily gotten, they are low in cost and low in processing power. And you don't require any pre-training to train the sound classification. While the limitation of the whole experiment is there is no noise filtering applied in the framework yet, and that will be part of the future research. And also we need to conduct a proper site experiment to test the visibility of the whole entire framework. Yeah, thank you. If you have any questions, let us know, please.
Thank you very much for joining us online and the nice presentation. We are 1 minute over time, but maybe I would like to open the floor for one question, perhaps. Give you the chance to do that. If not, I believe you have the contact information for the authors. You can reach out to them with any questions. No questions. Okay, great. Thank you so much. And moving on to the next part of the symposium, we have the